But we started thinking about what we now calling Graph-as-Policy. So rather than code as policy, we're now generating graphs and not raw code. And so the idea is we're going to automatically generate with an agent a computation graph. And that graph structure has a number of benefits because we can decompose it into nice clean modules or nodes. And each node has certain functionality, and then that opens the door to multi-agent coding because you can have each agent looking after each individual node, and also making sure that the nodes are compatible, that their inputs and outputs are clean, and they obey certain structural constraints that make this thing start to compile and assemble and work consistently. So you can have a subgraph of these nodes. You might call the perception subgraph, another set of nodes for motion planning, and then another set of nodes for grasping. Not just with one method of grasping, but with different methods of grasping. And so the problem definition for the Graph-as-Policy is we're calling it we're going to say that we have variational automation tasks. And this is a tuple that has a language description of what you want to get done, but also you get information that you can actually, you know what the environment is going to be. Because whether you're in a coffee shop or a logistics warehouse, you know what the environment is. So you can take that as input. That's very valuable. You know the geometry, you know the coordinate frames. You also know the robot. You know things about the sensors. So all that can go in. And then there's a set of objects. Again, you can formalize that in a variety of different ways, but you know the set of objects, the class of objects you're going to be dealing with. And then there's a state space, which is going to be when you're actually performing one of the variational automation tasks, you're going to then be working within a state space of a subset of the objects and robot states. Then there's a belief space, which is all the possible states that you can encounter. And again, you can characterize that, maybe with a distribution. And finally, there's a reward function. It characterizes basically how well that system is going to work, basically what you want it to accomplish. And the output then is going to be a graph with a number of vertices or nodes and edges. And that's going to be used to instantiate a policy that's going to take the task and look at different for each state, generate appropriate actions. So here is what it looks like in an architectural diagram. Basically, this thing is what's called a harness, meaning that the harness is a way of basically driving this wild beast that's the agent, or multiple agents. You need a way to get them to do what you want. So that's why it's called a harness. But the gap harness basically takes in the geometry, this task definition that I just showed you, and also the language description, and it generates it breaks things down into segments. Again, it does that with the power of the LLM, and then assembles that into this computation graph, initial computation graph. And then it instantiates that with parameters based on the geometry of the objects that it may see. And then basically it goes into a self-learning mode where you're iterating over these graphs. You're trying to improve the graph by executing the resulting graph and seeing how it performs, and then modifying the graph. And these agentic systems are very good at this kind of iteration. So what you then get out of that is a G star, the optimal graph, the best one you can do, the one that performs the best, and then that gets shipped out to the robot itself. And that's where you have a graph executor, just like you have with ROS computation graphs, and that can run on a very, very lightweight computational system. So you don't need the power of the GPUs or LLMs and all that at that point. And so what you're trying to do is find this graph that will maximize your performance.
本演讲实录已收录至雷锋网 ICRA 2026深度专区，现已全面上线。专区不仅全面收录了重磅论文的工程化解读、专家前沿演讲，更将持续更新前方记者的第一手会议动态。扫描下方二维码或进入雷锋网ICRA专区即可查看。